talk today about various applications in ADS CFT where the CFT, where the boundary theory is living on a space-time that has a boundary. And so you should feel free to stop me and ask questions. I have slides, so it seems a little bit formal, but I'd be happy to talk about anything, and I can write on the screen, I think, as well. So the idea here, just in terms of setup, is that we can think about holographic CFTs or any CFTs and consider those things to be defined on some space with a boundary. And in making this definition, one needs to make some choice of what happens at the boundary. And so, for example, if I were talking about a free scalar field, then we could choose Neumann or boundary or Dirichlet boundary conditions at the boundary. But in more complicated situations with a lot of degrees of freedom, there are typically many possible choices of what can happen at the boundary. And so in general, a way to think about these is that some of the boundary conditions that you can choose would preserve the conformal invariance of your theory. So if you, say, had your CFT defined on a half space, and then you chose the right boundary condition, then that theory with that boundary condition would continue to have scaling invariance and sort of some part of the original conformal symmetry. More precisely, it's sort of the conformal symmetry that a theory in one less dimension would have. And more generally, we can have boundary conditions that would be sort of boundary RG flows between these different conformally invariant boundary conditions, just as the quantum field theories themselves can be RG flows from some UV CFT to an IR CFT. Another thing we can have, sometimes it's possible to think of not just defining some boundary conditions for the degrees of freedom that you already have, but actually think about there being extra degrees of freedom on the boundary. Sometimes a lot of extra degrees of freedom on the boundary. And so in string theory, for example, you can have situations where you have, say, D3 branes that are ending on some D5 branes or NS5 branes. Then you can also have additional degrees of freedom associated with the boundary. So for example, if you have some various stacks of D5s or NS5s, you can have additional branes stretching between those. And then in the low energy theory of that system, you would have a bulk CFT and then a set of boundary degrees of freedom as well. Okay. And so in this talk, I'm going to be thinking about situations where our CFT is holographic and we have an edge or a boundary of the space that the CFT is living on. And we want to understand what would the bulk description of that be? What would the gravity description of this situation be? And so here I've drawn a cartoon. So if we didn't have this boundary, then we would have a CFT, and then the dual would be some asymptotically, well, would be ADS space-time if we're talking about the vacuum state, or generally some asymptotically ADS space-time. And now we've introduced this boundary in the CFT, and so something has to happen in the bulk to reflect that. And the kind of cartoon picture of this is that we can imagine this boundary of our CFT extending into the bulk in some way. And generally, I'm going to call that an end of the world brane. Okay, so if you had a ADS spacetime before, then now, well, some of that is missing because you've removed a bunch of the previous CFT degrees of freedom, and so somehow the previous ADS space has to end in the bulk here. And now, so this picture is kind of maybe a bottom-up picture of what's really going on. So in a more microscopic perspective, there is not necessarily anything sharp that terminates the space-time. What can happen microscopically is that you have, say, ADS times some internal space, and then as you approach this this place here, that could indicate the internal space smoothly degenerating. So a very simple example of this kind of thing would be in the bubble of nothing space-time, where you have, say, one extra circular dimension. And then a bubble of nothing is a place where that circular direction smoothly pinches off. And so from the lower dimensional perspective, it's like you have an end of the world brane there, but really it's nothing, there's nothing physical, it's not an actual brane there, it's just a part of your higher dimensional geometry. Okay. And so, you know, in general, one could try to, question?
Yeah, is space always sort of cut off at some finite distance? Could it be like sort of like there's a potential which makes it harder and harder to go further away, but you could, with enough energy, go infinite distance away in ADS, even though it's finite on the boundary?
Yeah, I mean, I think, so, you know, of course, it's an infinite distance to this ADS boundary, and in general, yeah. So yeah. I think you should think of it as being a finite distance to this red region. I mean, at least in the examples that. So I was going to say, we have many microscopic examples where these solutions are known explicitly. Yeah. So for, say, n equals 4 supersymmetric Yang-Mills theory, there are all these half supersymmetric boundary conditions that you can choose, and then it's known that you have all these solutions of type 2b supergravity that are dual to these things, and you know, again, they're sort of complicated, but from the lower dimensional perspective, I would say that you should think of it as there being, you know, sort of a finite distance to this place. Okay, so it's still an infinite distance to the places that are asymptotically ADS, but generally the places in the bulk that are, you know, an infinite distance away correspond to the actual asymptotic boundary.
Right. I was wondering whether the effective distance could be dynamical, in the sense that if you push harder with more energy, you go further in the bulk. That it's not really like a cutoff, more like a potential.
I mean, so I mean, I think there is if you fix the state, then there is a bulk geometry in the usual way. So, you know, these are just some solution of type 2b supergravity, for example. But it is an important point that this end of the world brane, it's a dynamical object. I mean, so if you modify the state, or if you do have some excitation in here, then certainly this end of the world brane can alter, and so depending on the state of your CFT with the boundary, you would have a different geometry, and in some of those geometries, indeed, the end of the, you know, effectively this thing would be further away.
Okay, thank you.
Yeah. Okay. Okay, so again, you know, there's this, say, top-down way that we could study these situations, and generally I'm not going to do that in this talk. Rather, I'll try to study these situations in more of a bottom-up approach, where, you know, in the typical thing we do in ADS CFT would be to sort of choose some convenient gravitational action, so Einstein gravity, maybe with some scalar fields, and then study the physics of that and understand what it can teach us about the field theory, and then, you know, later you could try to come up with some top-down version. Similarly, we can think of choosing a bulk action and then choosing some action that's going to represent the physics of this end of the world brane. And again, one can start with the simplest sorts of actions, and so the simplest thing we could imagine is just having having some cosmological constant term. So like integral of the square root of the induced metric times a constant. And that would be, that constant you could think of as a tension for this end of the world brane. So that's the very simplest term you could add in a bottom-up kind of action for these end of the world branes. And then you could imagine sort of more complicated terms as well. You could have couplings to scalar fields in the bulk and so forth. So the most important thing that I'll talk about is just that one parameter, which is the tension parameter. And so I should mention that Takinagi made an interesting observation about this tension parameter. Okay, so if we think about just the very simplest sorts of solutions, where you would have just a CFT on a half space, and then some boundary, and we try to model that in the bulk by a solution to our gravity equations with an end of the world brane with some particular tension, then the solution looks like this. If we use Poincaré coordinates for ADS, then this end of the world brane just goes off at some particular angle. And the angle increases as the tension of the brane increases. And what Takinagi pointed out in a paper some time ago is that the tension is positively related to a quantity known as boundary entropy for the CFT. And so here my pictures are relevant to 1+1 dimensional CFTs, but there's a similar story in higher dimensions. So the 1+1 dimensional story is that just as you have a central charge that is related to the number of degrees of freedom of your bulk CFT, then there's also some parameter associated with your boundary condition that you can think of as a boundary analog of the central charge. One place that this shows up is that if you calculate the entanglement entropy in the vacuum state of an interval of length L, then the answer to that universally in CFTs is equal to something that looks like the bulk answer. So it's C/6 times this log of twice this distance. And then there's a boundary contribution, which we often call log of G. So this thing is what's known as the boundary entropy. And roughly you can think of it as some measure of the number of boundary degrees of freedom in the same way that the central charge is a measure of the number of degrees of freedom in the bulk. Okay. And there's an analogous quantity for 2+1 or 3+1 dimensional conformal field theories that would also, for example, show up in the entanglement entropy. And okay, so this is sort of a universal formula that you would get for the entanglement entropy of this interval in CFT. And then on the gravity side, if you try to calculate the entanglement entropy using the standard holographic prescription, which is the Ryu-Takinagi formula, what happens is that you have an RT surface that extends into the bulk, and then the minimal area surface typically ends on the brane like that. Okay. And so then you find that this part of the surface, if you calculate the area, this part of the surface gives you this term, and this part of the surface in the gravity picture, that turns out to be or positively related to the tension parameter. And if you compare the two answers, then you find that this function of the tension is equal to the boundary entropy. Okay, so the main thing to take away from this analysis is that we have this parameter in the bottom-up gravity action we're using to model our end of the world brane, and the parameter gives us an indication of how many degrees of freedom are associated with our boundary in the CFT with a boundary.
Sorry, Mark. It looks like from your diagram that the t goes to infinity limit gives you all of ADS space. Is that right?
Yeah. So if in this case, so this parameter t is sort of it's actually t going to 1 in this way of parameterizing things. This angle would then, apparently give you back everything you had before. Now, one of the that would correspond to sort of this infinite boundary entropy here. So one of the interesting questions is, what possible values of boundary entropy do we have in a CFT? Probably it's not so. So for, say, the Ising CFT, there are 3 known choices of boundary conditions, and they come along with sort of 3 values of this boundary entropy. So for some holographic CFT, then again, I would expect there to be some specific set of choices for this boundary entropy, and not necessarily some choice that would, or not necessarily a sequence of them that would go off to infinity. But so depending on the actual CFT, then the allowed values of this tension parameter would be specified, and maybe we can't get all the way to getting all of ADS back, but it does seem like if you can have large values of this, then this surface can kind of end up at a large angle and seem to give you a lot of the space-time back that you had before. So that'll actually be important for us.
Okay. Do you have an equation relating theta and t?
Yeah, it's just sine theta equals t. So it's very simple.
Yeah. Okay, thanks.
Sorry, can I ask a small?
Yeah.
Yeah. So basically, this end of the world brane that you're talking about can also be viewed as a boundary of the bulk region, right? It's one of the boundaries. So I was wondering what kind of. So are you going to put boundary conditions here as far as the bulk fields are concerned? And is that independent data, or what is going to?
So right, good question. So it's in the microscopic picture, the end of the world brane, you should think of it as being some interior points in the geometry. So actually one point that I should have mentioned is that, this RT surface, it's supposed to be homologous to this, which means that, this together with this should form the boundary of some region of the bulk. And you might have said, well, this is a part of the boundary of that region that we're leaving out, but for the purposes of this homology condition, you should think of these red points as being interior points in the geometry, because in the higher dimensional perspective, they would be. Yeah, in terms of the effective description in lower dimensions, then there should be some specification of some boundary conditions. So for example, maybe you should have something like Neumann boundary conditions on fields to prevent energy from flowing out through this surface.
Is that a choice? Is that a choice, or it's somehow also determined?
So yeah, I think it's probably physically necessary not to lose energy through this surface. We have some choices in terms of the actual action that we pick, but I would say that so far we're just sort of trying to do something physically reasonable, and then I guess ultimately if we had some microscopic story, it would probably specify exactly what we're allowed to do.
I see. All right, thanks.
Yeah.
Mark, do you expect the values of GB to be discrete in general?
Yeah, that's a good question. So I don't know. I think for the simple CFTs where these things are known, then they're discrete. also in the example where you have n equals 4 supersymmetric Yang-Niels theory, and you look at the boundary conditions that preserves supersymmetry, then those also correspond to sort of various ways of ending D3 branes on various stacks of D5 branes, so that they're sort of discrete as well. But I should say we could have, it's possible to consider boundary conditions that are something like superpositions of other boundary conditions, and in that case, then you would have some continuous parameters.
Thank you.
Okay, I'll continue. Okay, so actually, by the way, when should I sort of try to aim to finish? Should I adjust my timing or?
So the seminar is usually for an hour, but
Yes.
the timing is flexible, and we often do go over considerably. So
Okay.
Yeah, I would suggest maybe plan for an hour.
Okay. So I'll try to sort of give the seminar I would have given, and that should be less than an hour. Okay, great. Okay, so I want to talk about another more recent calculation. So this older work of Takenagi considered the calculation of the entanglement entropy for an interval, including the boundary and the holographic calculation that corresponds to that. Fairly recently, with Jamie Sully and my graduate student David Wakeham, we had a paper that generalizes this to the case where we have an interval which is separated from the boundary. And so I'm going to tell you about that calculation, and then there will be many applications of this later on. Okay, so this is sort of fairly quick. You have an interesting story when you have the interval. So again, we're thinking about the vacuum state of a CFT with some boundary. Here, I'm just talking about 1 + 1 dimensions. And now I want to think about an interval which is separated from the boundary like this. And so there's an interesting kind of prediction from the gravity side, which is that you should have a phase transition in the entanglement entropy if you vary the location of this interval. And so that's shown in the pictures here. So the interval is far away from the boundary. Then the minimal area extremal surface is one that doesn't touch the boundary, just goes through the bulk. Whereas if the interval is moved close to the boundary, then you have this other choice, which is a disconnected Ryu-Takenagi surface, and so that one has the minimum area as A is moved closer to the boundary. Okay. So this one has the interesting feature that sort of saturates one of these entropy inequalities, that the entropy here is just the same as, this is the area of this surface calculated the holographic entanglement entropy of the region B, and the area of this surface calculated the holographic entanglement entropy of the region A union B. And so this phase is sort of special in that it suggests that a particular kind of entropy inequality is exactly separated. In general, this is one of these something like subadditivity or strong subadditivity. There's something called the Araki-Lieb inequality, which is like a triangle inequality for entanglement entropies. And so generally this would be an inequality, but it's sort of gravity predicts that it's saturated to leading order in large N. Okay, so you have this interesting kind of gravity result where in this case it's a connected RT surface. In this case, it's a disconnected RT surface. One of the things that will be important later is that in this case, the what's known as the entanglement wedge of this region A, it includes a portion of this end of the world brane. Okay, and so one of the things that you could try to do is sort of check this prediction or try to understand this prediction in CFT language. So we can try to do the same calculation of entanglement entropy directly in the CFT. And if you're familiar with these things, then there's some replica trick calculation that you can do. So you start with the Renyi entropies and then take a limit as n goes to 1 to get entanglement entropy, and then to calculate the Renyi entropies. That corresponds to calculating the partition function of your CFT on some multi-sheeted surface where the sheets are glued along a cut, which is the region that you're interested in. Okay. And so this is the space that we want to calculate the partition function of our CFT on. These are the two cases as the interval gets closer or further away, and so in this case. So in general, when we calculate these partition functions in the CFT on the multi-sheeted surface, there's a way to do that using twist operators. And so I won't completely review this story since it's not essential for most of the rest of the talk. But basically, the partition function is equal to the 2-point function of this thing called the twist operator, which you can think of as an operator in the n copy CFT that inserts this gluing prescription. Okay, so there's this partition function we need to calculate the entanglement entropy. That translates into this 2-point function of these particular operators in the n copy version of our boundary CFT, and then the way that we can understand this phase transition that I mentioned in the previous slide is that there are different channels for which you can expand the 2-point function. Okay, so you can write the 2-point function of these twist operators either using a bulk operator product expansion to re-express the 2-point function in terms of a sum of 1-point functions, or you can use something called the boundary operator expansion, where any bulk operator can be expanded in terms of boundary operators that are localized to the boundary of our CFT. And so you have this other channel where first you express both of these bulk operators in terms of boundary operators, and then your bulk CFT sort of reduces to a sum of so your bulk 2-point function reduces to a sum of boundary 2-point functions. Okay, so both of these are just exact ways to express the 2-point function, just as we can express the 4-point function in different channels. And so the interesting thing is that if you then restrict these, so both of these involve some sum, this one over bulk operators, this one over boundary operators. If you restrict the sum here just to the vacuum, or sorry, the identity operator and Virasoro descendants of the identity operator, and then just look at what answer does that give you, it turns out that exactly gives you this answer on the gravity side for the situation where you've just modeled this end of the world brane as being purely gravitational with some tension. Okay, so there's sort of a direct CFT analog of that kind of very simple model that we've chosen on the bulk side. Okay, and similarly, if you just keep the identity operator on the boundary and Virasoro descendants of the identity operator on the boundary, then the 2-point function that you get in that calculation exactly reproduces this answer. Okay, now, okay, and so the the fact that so these answers that you get by sort of throwing away everything and just keeping the vacuum block contributions, that sort of shows up in a similar calculation for two intervals in a bulk CFT. So Hartman sort of showed that that the gravity answer that you get in that case, which also exhibits a similar phase transition, is exactly reproduced by just keeping these specific channel, the vacuum contribution to specific channels, and so if you sort of make the assumption on the CFT side that the full answer to your, in that case it's a 4-point function, is given by the vacuum block in some channel, then you kind of reproduce the gravity result. Okay, so there's a parallel thing here that we're saying, if it happens that the CFT result is always given by just the vacuum block in some channel, one of these two channels, then you kind of exactly reproduce this gravity answer with the simple kind of holographic prescription of putting attention on this end of the world brane. Okay, so you can think of it as kind of a prediction for some properties of the CFT based on what happens in the gravity side.
So this happens in a particular fixed cross ratio independent of the theory, or the 1-point function of the twist operator also comes in?
Yeah, so good. So the place where this transition happens, it depends on this boundary entropy. And so it's not universal in the sense that the 2-interval result for bulk CFTs is universal. Okay, and actually I should say more. I mean, in general, we don't expect the gravity picture to be this simple. So I should say, in general, we can have some scalar fields that are turned on that are sourced by this brane. That corresponds to the fact that you can have non-zero 1-point functions in a boundary CFT. So when I have a boundary, certain scalar operators might have a 1-point function. And so this answer, so the answer that you get for this connected phase here, it's generally going to be more complicated.
Even at C?
Say again?
Even at large C?
Yeah, even at large C, I mean, then you can have, if you have scalars turned on and back reaction, then the answer for this phase is going to be some complicated function of the length of the interval. Okay, and so that sort of suggests that in this channel, that vacuum block dominance is something fairly special that might happen in some special CFTs, some special holographic CFTs, but not all of them. But one of the interesting points is that in this channel, the answer is actually universal, even if the bulk is complicated. In this channel, you see that the answer to the entanglement entropy for this interval is equal to the entropy for this one plus the entropy of this one, and those had a universal form. Okay, so the kind of very robust prediction from the gravity theory is that for some, if this interval is close enough to the boundary, then on the CFT side, for pretty much any holographic CFT, we expect that this channel, just keeping the vacuum block, should give the right answer. Okay, and so in our paper we kind of translated that into more detailed conditions on the spectrum of operators in the CFT, the spectrum of bulk and boundary operators in the CFT.
Thank you.
Okay.
Mark?
Yeah.
Sorry, just a question.
Yeah.
So I'm just trying to understand, I understand this gravity picture and so on and so forth, and this domination in the replica path integral. but I'm trying to understand, what does it physically tell us? Is it that the intervals somehow closer to this boundary are more entangled with this boundary, whereas there is some kind of a length scale below, like, and if the interval is outside it, it is not entangled? I mean, what should I, if I have to phrase this in terms of entanglement directly in the CFT, what would I say?
Yeah, I mean, so you can look at this. You can look at this equality here, and so it basically suggests that if you the fact that SA is equal to this plus this, it's sort of saying if this interval is close enough to the boundary, then the entanglement, you can understand it as saying that the entanglement of the interval A with the rest of the system, you can think of it as being some more or less localized entanglement between degrees of freedom here and degrees of freedom here. Okay, so plus some entanglement between degrees of freedom here and sort of degrees of freedom in this boundary region. So if that were, I mean, if you could think of the entanglement as being sort of coming from two separate things, localized to near here and localized to near here, then this would be satisfied. So I think that's what the gravity is suggesting. Okay.
And that is not the case if the interval is far away from
that's right. Yeah, that's right.
But why would that be the case? I mean, if there's some
yeah, I mean, I think if it's far away, you might think that, okay, I mean, so yeah, I mean, in general, let's see. So, in general, this sort of thing is these sorts of entropies are not simply additive in sort of complicated quantum states, and so yeah, I don't know if I have a sort of deep reason for why it should be a sharp transition. But I guess it's just that if these two sides, yeah, I mean, if these two sides are, it's behaving like this, it's behaving like there's sort of not a strong connection between this side and over here.
Okay, maybe perhaps I can just rephrase the question a bit. So if I just want to think about this entanglement entropy as coming from some bell pairs, some bell pair, with one of them inside A, where will the other pairs be? Is there some?
So, I mean, if there's just a bunch of bell pairs from A out here, and then and then a bunch of bell pairs from B in here. Okay. Then this would be true. Let's see. So if you have more complicated kinds of entanglement, then that could fail. So if it is just this is sort of saying that the entanglement is like you just have some bell pairs from A out here and some bell pairs from A here. But I think more generally than the entanglement entropy doesn't have to look like that.
Okay, yeah. Thanks.
Okay, sure.
Sorry, Mark.
Sorry, just to add, I mean, just a follow-up of the question.
Yeah.
There's this big thread picture, which was developed by, Manton.
Yeah.
So now in that, if we try to take that picture, then presumably there would be big threads which are starting from A and ending on this end of world brane, right?
Well, I don't know if, I think the bit threads I think are supposed to end on the actual asymptotic boundary of the space.
Right.
So our actual degrees of freedom are just in the green region here.
Okay. Okay, so you're saying that if we run that through, then then we'll see that. So I think that can help in resolving this question about what are the naive bell pairs, right? Because you can think of the two ends of the bit threads as the things that are getting entangled, roughly, very roughly.
Okay.
Sorry,
yeah.
Just going back to the question that I asked, I didn't quite understand the universality of the dominance of the identity block in the disconnected phase.
Yeah, let me say that clearly. Okay. So what you notice in the disconnected phase, regardless of how complicated this geometry is, then the area of the RT surface is the sum of this area and the sum of this area. And this area is the one that computed the entanglement entropy of this region B. Okay. That has a universal answer. So for an interval which includes the boundary, then the answer for the entanglement entropy in any CFT is this.
But this
okay.
is also,
and similarly, this one, this one here is the thing that computed the entanglement entropy of A plus B. And that also is an interval that includes the boundary. So even if this is a complicated geometry, it's sort of clear that in the holographic calculation of entanglement entropy, that SA is equal to this plus this, and both of those are simple entanglement entropies of regions, including the boundary, which are simple. So we can write, a simple answer for the entanglement entropy of A, even without knowing the detailed geometry, just the fact that it's disconnected.
And in the connected phase, the entanglement entropy of A doesn't have a universal form.
That's right. So in the connected phase, in the simple model where we have a purely gravitational end of the world brane, then we can write that the entanglement entropy is equal to this because the bulk solution is sort of pure ADS3. But that's not expected to be true for any holographic CFT. And in particular, your end of the world brane could source some scalar fields. Those can back react on the geometry, and then the geometry of this RT surface can be very complicated.
Okay. But from the confirmed field theory point of view, this non-universality you are saying comes from the exchange of non-identity operators.
That's right. So that's right. So let me say, if you have a 1-point function if there's a scalar operator in your conformal field theory that has a 1-point function in the presence of this boundary, then you're going to have contributions. I mean, there's some more detailed argument, but we can argue that you're going to have contributions to this channel where you have non-identity operators contributing, or non-identity block operators contributing, and then those will change the answer.
So a priori, non-identity operators could also run in the boundary channel, right?
Yeah, that's right. So we could have, of course, we may not have expected this vacuum block dominance at all, but in this case, it seems that in this boundary channel, because the gravity calculation suggests a universal result, that suggests that this vacuum block does dominate in the boundary channel, at least when you're in this phase.
Okay, thank you.
Yeah. Okay. Okay, and just sort of one more quick thing that connects with some recent discussions. So if instead of trying to do a CFT calculation, if I tried to just do this multi-sheet partition function calculation directly in gravity, then there's an interesting result, which is that in this phase you can understand the difference between the two phases as being one where in the top phase the sort of gravity dual of this multi-sheeted CFT thing has, so you'll notice we have sort of n boundaries here, okay, and those extended to the bulk somehow. And in this phase, in the gravity calculation, those give you sort of n disconnected end of the world branes Whereas in this phase, on the gravity section, in the gravity picture, then you just have sort of some connected geometry. And so this is something like, people have been talking about these multi-boundary wormholes contributing to certain gravity calculations. So this is kind of like a multi-boundary or replica wormhole geometry for our end of the world brane. And that will be sort of, we're actually going to connect this to some of the black hole evaporation calculations that that people have been talking about. Okay, so
sorry,
yeah.
Mark, can you repeat this correspondence between the CFT picture and the pictures that you drew on the right side?
Okay, so if I wanted to do a gravity calculation of the n-sheeted partition function that I would use to calculate Renyi entropies, then I would try to find an asymptotically ADS geometry whose boundary is this. Okay, and now of course the boundary geometry has these, some n CFT boundaries. And so I guess in the pictures on the right, I've done some conformal transformation to map these lines to circles. Okay, and so here's a geometry. So the geometry of our CFT is now, after some conformal transformation, it's like a sphere with n circles removed. So there's these n red circles. Here I've done 3. I've done the 3 copy example in my picture. Okay. And then there's various ways you can imagine filling in that geometry. Okay. And so on the top, you've sort of filled in the sphere in such a way that the boundaries here fill into some connected. So we have connected surfaces. So we have these 3, disconnected surfaces. So we start with a sphere with 3 holes cut out of it, and then we fill in the sphere, and we sort of fill in the holes with an end of the world brane like this. Okay. But there's another kind of topology you can imagine, starting with a sphere with some holes cut out. We can actually fill in the sphere, but then, in understanding what does the end of the world brane do, it can connect up. So this red surface is supposed to be the end of the world brane, and inside that surface is just empty. So you see, this is a different topology that we could have for the bulk geometry contributing to our partition function. And the claim is that in this phase, the geometry is like this, whereas in this phase, the geometry is like this.
Thank you.
Mark,
Okay.
just to clarify, so in
Yes.
in these pictures that you're drawing with the sphere and so on and so forth, you're not showing the interval. You're just showing the boundary.
Yeah, I mean, so basically, like the interval. Yeah, I mean, the interval is what glues. Right, I can draw the interval. I think. Sorry. Somehow, okay. Yeah. Yeah. So the interval is like this. So there, imagine a point here, and then a point on the far side of the sphere, and then, okay. And so, so basically I've done some conformal. So each of these sheets is sort of 1/3 of this sphere. Okay. So you sort of see each of the sheets after this conformal transformation. This interval here sort of expands out into 2 sides, and then the boundary here is transformed to the circle. So the entire multi-boundary thing you can actually represent as sort of a single sphere, which is 3 parts glued together, and then 3 boundaries inside.
And a similar thing is true about the next sphere also, the lower diagram also.
Yeah, that's right. It's the same boundary geometry, and just a different way of filling it in the bulk.
Okay, thanks.
Okay. Okay, let me talk about the applications then. Okay, so let's see. Need to get rid of that. Okay, how do I get, oh, someone, okay. Someone cleared that for me. Thank you.
Sorry, I cleared it, yeah.
Thank you. All right. Okay, so I'm going to talk about various applications. Having a boundary in our CFT allows us to do a bunch of interesting things in holography. So let me just say, one general, very interesting thing that maybe if you just sort of take this away from this is maybe the most important thing in the talk, that if we add boundaries to our CFT in a holographic system, this seems to give some way of introducing dynamical boundaries in space-time on the gravity side. And so let me just indicate this with a cartoon. And so here on the left, we have some CFT, and then now this is the boundary of some asymptotically ADS geometry. Okay. Now what I want to imagine is introducing a boundary into that CFT, but now I'm going to introduce that as a circular boundary instead of a planar boundary. So I introduce this circular boundary. I remove all of the CFT degrees of freedom that were in the middle. And now my CFT is, it's this region, and then there's a red circle. And so typically, so I have to understand, what does that do on the gravity side? And so, somehow the space-time on the gravity side has to be such that the boundary of it is now this plane with a circle missing. And so just sort of topologically, often the way that will resolve itself is that you have something which we're describing as this end of the world brane. And in this kind of topology where you just cut out a circle, that should just fill in on itself. And so as I mentioned before, the microscopic picture of what's really going on here can differ depending on what is our microscopic CFT. But this is somehow giving us a part of our boundary which is dynamical. Okay, so we've replaced this rigid boundary that was there everywhere with, we sort of cut out some of the CFT degrees of freedom, maybe put some boundary degrees of freedom here. And then the interpretation on the gravity side is that part of our boundary now is maybe at finite distance from the bulk, and it's something which is dynamical, which can fluctuate. And so I think that's very interesting because it's one of the directions that we want to go in ADS CFT if we want to generalize and understand how to do quantum gravity, say, with closed universes or just more general situations than the gravity dual of some quantum field theory. This is sort of doing that, but just for part of your boundary. So we still have some rigid boundary, but it seems like we have some part of the boundary which is dynamical. Okay, so I think that's quite interesting on its own. And so coming back to a comment of Shiraz from before, one interesting thing we can do here is actually to imagine the case where we do the same thing here, but now we've added many boundary degrees of freedom. Okay, so in the 2D language, that would be log G maybe is much larger than C. So this is holographic, and then we also add a bunch of degrees of freedom here, which I want to imagine are also holographic. And so we can just remember what happened when you increase the number of boundary degrees of freedom. So you get more and more space. Remember that the angle increased, and so if you have this end of the world brane, which we can think of as a bubble in our former geometry, as I add boundary degrees of freedom, it seems like you get more and more space coming back. Okay. So it makes sense if you have more degrees of freedom there, then the gravity picture maybe has more space time. And so just, sort of very naively, if you're recovering more and more of your former ADS space, then it's almost like for a very large number of degrees of freedom, you've just sort of placed a cutoff in your ADS space, but only in some region of the boundary. Okay, so it's like you have most of ADS, and then in this one particular region of the boundary, you've cut off the UV and just replaced it with some brain. Okay, and so back 20 years ago, there was a lot of discussion about the physics of that situation where you start with ADS and then you place some cutoff close to the boundary. And it was understood that that end of the world brains like that exhibited a phenomenon of gravity localization that actually you can have effectively a sort of lower dimensional theory of gravity living on this brain, and you sort of think of it as part of the bulk, some mode of the bulk higher dimensional graviton acting as a nearly massless graviton in lower dimensions. Okay. And so this is quite interesting. So that was the Randall-Sundrum story, and so in this context of CFTs with boundaries, it's sort of giving us a way to realize this Randall-Sundrum picture, at least where your Randall-Sundrum brain is sort of localized, or where that Randall-Sundrum brain itself has some asymptotically ADS boundary. So we have this microscopic description here, and then we have the gravity dual is ADS and then some brain here. But then there's sort of also a third description where it's like you have your CFT, and then in this region it's like you have we've placed a cutoff just in this region. So we've just removed the asymptotic part of this region. We place a cutoff here, and now that cutoff CFT we should think of as being coupled to gravity, because this there's gravitational physics on that brain. And okay, and so you could ask, well, what is this gravity theory here that we get all of a sudden? And I guess a way to understand that is, a separate way to understand that is to say, well, let's think of the whole thing a different way. Let's think about not having these bulk degrees of freedom at all. What if we just had the boundary degrees of freedom here? There's a lot of them. We could imagine they're holographic. Then the degrees of freedom on this circle would be dual to some gravity theory. And I guess you can think of that as the gravitational theory that's then coupled to this cutoff CFT. So you could start with some gravity theory in if say this is d-1 dimensions, this would be a d-dimensional gravity theory. And now you can add back in these bulk CFT degrees of freedom. Okay, so then you would have a d-dimensional gravity theory. And now you sort of, by adding these bulk CFT degrees of freedom, then you have this effective picture here. And you've got this sort of higher dimensional picture. This is the full holographic picture where your former gravity theory is now kind of an end of the world brain, and then you coupled in extra bulk degrees of freedom.
So Mark,
yeah.
When you talk of CFT, you mean the CFT in the green region? There are the same degrees of freedom living also in the red region, which are then coupled to gravity.
Yeah. So I guess I'm saying, of course, in the microscopic picture, you only have the CFT degrees of freedom here, and then you have some boundary degrees of freedom. Okay. But if this is the right picture, so the holographic picture should be something like this. And if this is the right picture where that end of the world brain is getting closer and closer to the original ADS boundary, then it looks like you're kind of getting back the degrees of freedom of your CFT that you cut out somehow. So because the ADS space kind of fills itself in, it kind of looks like you're getting back some of your CFT that was missing.
That geometrically you are approaching that point, but the degrees of freedom living on this pushed in part were never that of the CFT, right? They were always that of the bulk coupled to some gravity theory dual to, let's say, the boundary theory. But I don't quite see. So, for example, in the green region, if you start with let's say free CFT or something, then I don't see how the free field would start living on this red region.
Yeah, I mean, I'm sort of appealing to some just, what everyone always said about the Randall-Sundrum picture. If you have some Planck brane, which is so if instead of having the brane localized here, if I had a gravity picture where you have ADS space and then this brane kind of lives everywhere as a cutoff Planck brane cutting off the UV, then people said, well, you can understand that as being a cutoff CFT coupled to the gravitational dynamics of that brane. So I'm just saying that, but I'm saying now that Planck brane is only localized in some region.
Okay.
Sorry, Mark, following up, if this intuitive picture, if the intuitive picture that the pink region is just the CFT in the pink region coupled to gravity is just the gravity dual of the boundary CFT, if that is sort of can be made really precise, will it suggest that there's sort of one-to-one correspondence between possible boundary degrees of freedom that can be consistently coupled with the conformal field theory and the conformal field theory itself? Because the boundary degrees of freedom would have to know that it would have to reproduce that conformal field theory that it was coupled to.
Yeah, I mean, let's see. So
if you could add the same boundary,
something about any, so I'm not sure, it could be something, kind of a consistency condition for these boundary conditions.
Right.
I can have different physics here. Maybe there are many choices of boundary condition. They all give you sort of different physics in terms of the action of this end of the world brane. But all of them are somehow consistent with the original CFT in a certain way, and that translates to a compatibility condition on the gravity side. I mean, yeah, something like that.
Right. But you could imagine that you could add the same boundary degrees of freedom, same large number of boundary degrees of freedom to two different CFTs as on the boundaries of two different CFTs. And then you couldn't get the bulk dual of the same boundary degrees of freedom to be both those CFTs. So
yeah, I mean, I mean, I think, of course, this picture is somewhat imprecise. In a real microscopic example, I guess this brane would sort of source some bulk fields here. So as you got closer to the brane, I guess depending on your choice of boundary condition, the physics might be somewhat different. So when we say, cut off CFT, of course, there are many ways to cut off a CFT. And maybe this is just saying it's some way of consistently coupling these deep interior degrees of freedom out to these brane degrees of freedom.
Okay, good, thanks.
Okay.
Can I ask a question before you proceed, Mark?
Yes.
Hi,
sure.
this is Spenta.
Hi, Spenta.
Hi. So if I look at the SYK model, whose effective theory is, of course, not a conformal field theory, but if you look at the pure states description that was developed by Kurkulu and Maldacena, the end of the world brane is introduced to account for the fact that they have these these states, the BSL states, microscopic states of the at low energies of the SYK model. So somehow your picture doesn't seem to be a bit. It's a bit different from that, because the end of the world brane is sourced by the fact that you have this state to work with rather than just the ordinary vacuum amplitudes.
Yeah, I mean, actually, so I'm going to talk about something very shortly that's entirely parallel to Korkolu and Moldacena.
Okay.
So maybe it'll be helpful to see that, and then if you want, you can ask your question
All right.
again.
Sure,
Okay.
sure. Thanks.
Okay. So yeah, I'm running out of time, so I'll try to be relatively brief. I just want to show you a few more pictures of sort of interesting applications of all of this. And so one of the interesting applications that I talked about a while ago with Moshe Razali and Jamie Sully and my student David was, related to these models of black hole evaporation and holography, where one starts with some holographic system in a high energy state that would normally be dual to a black hole in equilibrium with its Hawking radiation. And then one imagines coupling that system to some auxiliary system so that now the black hole can evaporate, that kind of the information from the black hole can escape into this auxiliary system. And so I guess the thing we pointed out, inspired by all of these people, was that, well, this setup with, starting with a holographic system and now thinking of that as a set of kind of boundary degrees of freedom for some bulk CFT, that's a nice way to model these evaporating black holes, or it's a nice way to set up this holographic picture of black hole evaporation. And here, we think of there being maybe many more local degrees of freedom in our boundary system than in the bulk system, but we could still have it so that the bulk system is holographic. Okay, so the picture might be, you start with just the red degrees of freedom. They're in some high energy state, and so it describes a black hole in our lower dimensional gravity system. But now we want to add in these CFT degrees of freedom around that, and then the black hole can now evaporate because you have a bunch of energy localized here, which can leak out into the bulk degrees of freedom. And the amount of time it takes for that to happen actually is controlled by the ratio of the bulk central charge and the boundary entropy. Okay, so if you have relatively few bulk degrees of freedom, then the black hole lasts a long time, and so it's kind of more like an ordinary black hole evaporation. Okay, and so one of the interesting things that all of these people talked about, and that we just sort of wanted to understand in our context, was to look at how does the entropy of the radiation system evolve with time. Okay, so the black hole information paradox is related to the fact that a naive calculation suggests that the entropy of the radiation system keeps increasing, whereas the unitary evolution picture suggests that it should increase and then decrease again. And so, like in those models, what we find, so using this setup, one of the nice things about this setup is that you can have sort of an entirely holographic picture, and that was suggested by this paper by Almeri, Mahajan, Maldacena, and Zhao. So they were talking about a system where you have something very similar to this, where you have some holographic system, some gravitational theory, and then coupling that to an auxiliary field theory. And so our setup kind of gives or we thought sort of a more concrete microscopic picture of what they were trying to do, most of the ideas were there in this paper. So what you want to do is just study the evolution of entanglement entropy in this sort of setup. And I'm going to skip some of the details.
Sorry, Mark, can I just ask a question?
Yeah.
So in your previous slide.
Yeah.
So perhaps I should have asked this before. So from the gravity point of view, you're putting some kind of an absorbing boundary condition on this red side. Is that?
Yeah. Yeah. So I think in this picture here, so this is sort of the effective gravity picture where you have your sort of CFT coupled to gravity in the middle region, and then you just have a field theory on the outside. And so now, from that point of view, it's an absorbing boundary condition, or at least partly absorbing, because you can have energy leaking out into these CFT degrees of freedom, and then it's sort of lost forever.
Okay, thanks.
Yeah. Okay. Yeah. Okay. Let me just set this up. So instead of, we could try to do that that calculation exactly in the holographic setup. What we were able to do in most detail was sort of the 1+1 dimensional version of this, where the red circle is just a 0-dimensional sphere, so sort of 2 points, and then the green is a line. So this is very analogous to what was in the paper of Valmeri et al. And so the idea would be to start out with some situation where you have a bunch of energy in these degrees of freedom, and then it would evaporate. But actually, what we realized is that there's an even simpler setup where you actually just instead of having the surrounding region in the vacuum state, you can actually just have the entire thing in a thermal state. So there's still kind of a version of the information paradox that you can set up even if the energy density in the system doesn't really evolve with time. So the setup is actually that you just have, here's our boundary conformal field theory, and then I have the thermal field double of that with some other boundary conformal field theory. So this is like a two-sided 2D black hole, and then it's coupled to some CFT degrees of freedom. And then we want to calculate the entanglement entropy of the region exterior to, sorry, there it is. So we want to calculate the entanglement entropy of this region exterior to, at some distance A from these degrees of freedom, which we're thinking of as our original degrees of freedom describing our black hole. And okay, so we can set this up, and there's some gravity dual of this whole thing, and you can use holographic calculations of the entanglement entropy. I don't have time to go into all of the details, but basically what happens is that if you sort of naively calculate the entanglement entropy of this region, then even though the whole system is kind of in thermal equilibrium, the entropy actually increases. So the entanglement entropy of this black region, it increases, and naively it kind of increases forever. So this is the, oops, okay, this is the picture here. So there's some gravitational, there's some geometry dual to this. We're calculating entanglement entropy by some RT surface areas. And so if you just kind of take the naive the simplest RT surfaces, they suggest some picture where the entanglement of this radiation system kind of keeps increasing forever. But if you're more careful, then there's some picture where actually the correct RT surfaces make a transition from some connected RT surface to a disconnected RT surface. Okay, and then, oops, and then the prediction is that, so the original answer where the entropy keeps increasing forever is kind of paradoxical, because, you know, it's suggesting the black hole. So actually, first, why is the entropy changing at all? And there the picture is that we start out in a state where the two sides are entangled with each other, but more or less you can think of like these degrees of freedom as being entangled with these degrees of freedom. So it's like you start with a thermal field double of your lower dimensional CFT, and so the black hole degrees of freedom are mostly entangled with the second copy of the black hole degrees of freedom, and not with the radiation system. And then you allow this thing to evolve with time, and so then the black hole, even though it's not giving up any energy because it's already in thermal equilibrium with the surrounding system, it's becoming entangled with the, so it's kind of sharing information with the surrounding region. And so there's an increase in entanglement between these degrees of freedom and these ones. Okay, but the naive picture shows that entanglement increases forever. And then but in the corrected picture, if you use the right RT surface, then it eventually stops increasing and flattens. And yeah.
In the earlier part of the talk, you did talk about changing of this RT surface, but that was as a function of A.
That's right. So
now,
this is
somehow the RT surface.
Yeah. Now it's a function of time.
Is there a that I could see that essentially? I mean, I don't know. That would make me expect this type of a transition from the previous intuition.
Yeah. So okay, let me kind of jump to that. If someone could erase my screen again, that would be great. Okay, thank you. Right. Yeah, so that was a point was going to be that, you know, this calculation that we needed to do in this whole black hole story, it's just related. I won't go into the details. It's related by some conformal transformation to the same calculation that we did before. You know, so here we have, this is some path integral setting up the thermal field double of two boundary CFTs. And then this is the region that we're calculating the entanglement entropy of. And by some conformal transformation, I can map the circle to a line, and the entanglement entropy calculation gets mapped to the calculation of twist operators in these locations. And so basically it's the same, you know, if I think about just in general, the calculation of the 2-point function of twist operators for a CFT with a boundary, then in the space of locations of those twist operators, you know, which in general could depend on both Euclidean and Lorentzian time, then there's this phase transition that happens. And so in some situations, you can cross the phase boundary by varying a parameter that's interpreted as a spatial position, but you can also cross the phase boundary by varying a parameter that is a Lorentzian time. And so it's just kind of in general the space of when you're calculating this 2-point function of twist operators for an n-copy boundary conformal field theory, then the key point is that you can have this phase transition.
So it's just the cross ratio that matters, and changing time also lets you change the cross ratio. So
yeah,
just like changing A would, right?
There's a question. Mark, can I ask a question?
Yeah, absolutely.
Yeah. So in this calculation, you treated this, you know, this red line just as a boundary condition, rather than, you know, actually there is some, you know, some dynamics, some SYK model or something that is there in the thing. So they don't quite amount to just a boundary condition, because there's an entire Hilbert space of states in the SY.
Well, so I mean, I did a gravity calculation. Yeah, let me go back. I mean, it was a boundary condition, but it was really, I really wanted to think about the case where there are lots of degrees of freedom here.
Right.
Okay. So, you know, in order to get, I should have said that this transition happens at a certain time, which we think of as the page time. And for that to be large, what I need is for the number of boundary degrees of freedom to be large compared with the number of bulk degrees of freedom.
I realize that, but
yeah.
I'm talking about the CFT calculation. The CFT calculation, you know, in order to use Calabrese-Ricciardi like formulas, you know, you really have to use, you know, formulas like something in which you have a CFT with a boundary conditions, not boundary degrees of freedom. I mean, they, of course, you use the log GB coming from SYK, but that's just one number. You know, I would normally expect that you know, there's a whole dynamics of this SYK model, and depending on the coupling between your SYK and the Barth degrees of freedom, you know, you might not have you know, the SYK or whatever that model is being reflected just as a boundary condition on the Barth. It's more than just a boundary condition. So that's what
I read. So the maybe the two-dimensional model, it's okay. So let me step back and say, certainly in higher dimensions, when we draw this picture, then it's possible to have sort of a full holographic CFT here on the boundary, with lots of degrees of freedom, and then, you know, the analog of the boundary entropy would really be something like the central charge of that higher dimensional CFT.
Right.
Now, in the low dimensional example where the calculations are easy, I agree, it's not as clear that, you know, I can have lots of degrees of freedom here, or so I have this boundary entropy parameter, and I was saying that the large values, the larger that is, somehow it's like having more degrees of freedom on the boundary. So I don't really know in two-dimensional holographic CFTs if it's possible to have a lot of boundary degrees of freedom.
I wanted to make a point that these two red dots that you're talking about, suppose we have the, you know, two questions. There is no conformal field theory really there, at least as far as I know. The SYK model is not a conformal field theory. In fact, it's a reflection of the violation of conformal invariance. So, so that's one point why I think the model is in lower dimensions is a bit different, at least, from the higher dimensional discussion, in which you have a conformal field theory and you have these nice twist operators and their Green's functions, etc. The other one question I have is that, do you know of any conformal system which can holographically produce the ADS2 spacetime? See, we know of SYK that does it, which violates conformal invariance. Do you know of any system which is conformal and still holographic to ADS2 in 1+1 dimensions?
Yeah, I mean, in this case, it's like the, you know, in the full model, we have these slices that are ADS2, but of course the whole geometry is ADS3, or you know, ADS3 possibly with other fields. So I guess in our example, I mean, I wouldn't say that it's just a thing dual to ADS2, and I'm not sure how to do that. I think that the holographic calculation, if we could do the higher dimensional one, I mean, the only reason why we're doing this lower dimensional one is that, you know, I can write down nice analytic formulas.
Yes.
I'm pretty certain that I could do this with solving some PDEs. I could do the same holographic calculation starting in higher dimensions. So now it would actually be a circle or a sphere, and then I would have degrees of freedom out here. And I would think of, say, the thermofield double of this thing with another copy. I think I could repeat the whole thing and find similar results. Actually, I think yeah, Santos and a collaborator did something along these lines. I think it was a toroidal kind of system rather than a sphere. So there was some follow up in higher dimensions where they kind of ended up reaching the same conclusions. So I mean, I agree. Like the 1 + 1 dimensional system is not sort of ideal in that the boundary system here is not really a CFT like we would ideally want to replicate these pictures.
Yes.
But I think
Yes.
that the holographic model that we're using to study this is going to be quite similar to the higher dimensional versions of the holographic model.
Yeah.
I mean, and it's interesting that, you know, nevertheless, even though the CFT is sort of maybe simpler than we want, we can still see that there should be, even in this low dimensional setting, there should be this phase transition that we need in order to get this turning over of the page curve.
Okay, thank you.
Okay. Okay, so the final thing I'll just mention quickly, you know, we were talking about just the general idea that introducing the boundaries for your CFT gives you some kind of dynamical boundary for part of your bulk geometry. And so far, that dynamical boundary geometry, well, it itself had a boundary that sort of ended up connecting with our ADS asymptotics. And so it's interesting to ask whether we can describe situations where these end of the world branes, you know, which sometimes have their own intrinsic gravitational dynamics, whether those could be something like closed universes where you could have dynamical end of the world branes with no boundary, possibly with localized gravity. And so that would be sort of a step towards being able to describe quantum gravity or for cosmological spacetimes. So if we could at least describe the dynamics of spacetime boundaries, that would be interesting. And so I'll just mention, and this is what connects with Kurkulu and Maldacena. So I'll just mention this. So here, the way to do that is to, again, introduce a boundary to our CFT in the context of ADS CFT. But now the boundary is sort of in the Euclidean past. Okay, so we have some path integral. So this picture is supposed to indicate, starting with the path integral that would generate the vacuum state of your CFT on a sphere. Okay, so a semi-infinite Euclidean time direction. And now we chop that off, and we have a path integral where in the Euclidean past here we've introduced this boundary condition and possibly boundary degrees of freedom of some lower dimensional CFT. Okay. And then that path integral gives us some particular state of our CFT on the sphere that depends on our choice of boundary and boundary degrees of freedom and on this parameter tau 0. Okay. And so, again, we can study what is the gravity dual of that state. It's for small tau 0 at some high energy state of our CFT. And there's some recipe that you can follow to actually understand what is the Lorentzian geometry dual to this state. It's some time-dependent Lorentzian geometry. And I'll just skip ahead to what it looks like. And so it's a black hole geometry that's sort of outside the horizon, just looks like a Schwarzschild black hole. So this is probably the best picture to look at. This is the space-time picture of the dual of a state like this. And so it's outside the horizon, looks like this, just a regular black hole, static. But then behind the horizon, you have the appearance of this end of the world brane. Okay, so So there's a Euclidean geometry where the end of the world brane connects to the past Euclidean boundary and the future Euclidean boundary. But then in the Lorentzian geometry, it just looks like this, where you have your black hole geometry, you have a horizon. Behind the horizon, there's an end of the world brane. It's spherical. And as a function of time, that end of the world brane has a geometry that looks like this. So it comes out of the past horizon and goes into the future horizon. So it seems very interesting that you have these CFT states. If this is all correct, you have these states of your favorite holographic CFT on a sphere that in the bulk look like a black hole, but if you go behind the horizon, now there's this end of the world brane, and the end of the world brane itself has no boundary, it's dynamical, and its world volume is some sort of cosmological space-time. And I guess what's more interesting is to imagine the possibility that this brane could be far enough out, or have enough of the ADS space in the second asymptotic region, so that Randall-Sundrum phenomenology takes over and you actually have some localized gravity. So maybe you can even have a state of a holographic CFT, some particular time-dependent state, which is secretly describing this cosmological physics on an end of the world brane behind the horizon. And I am going to, so there's some story about how do you probe the physics of that brane behind the horizon. One way to do it is using entanglement entropy. There's some similar prediction of a phase transition. That's again related to the same CFT calculation. And I think that that's probably a good place to stop. Okay, so just a sort of a summary. I think the main interesting thing is that you can study holographic CFTs on spacetimes with boundaries. Sometimes you can add extra holographic degrees of freedom on those boundaries, and that gives you a bunch of new tools to study interesting applications in holography. One of the new things that it seems to allow you to do is to introduce some dynamical components to your space-time boundary, possibly giving you microscopic models of things like Randall-Sundrum physics. It gives us interesting models of evaporating black holes, of microstates with some behind the horizon geometry. And there are other applications that I haven't had time to talk about, but I feel like there's a lot of possible things to do in the future.
Let's all thank Mark by clapping, unmute ourselves. Okay, questions?
Mark,
yes.
About your end of the world branes for corresponding to the states, the last part
yes.
of your talk.
Yeah.
Two or three questions. First, what sets the effective tension of these branes?
So again, the idea is that it should be related to like the boundary entropy of our boundary condition or our boundary degrees of freedom. If I add more boundary degrees of freedom back here, then that would correspond to a higher tension. And that higher tension, I should say, it pushes this brane further past the horizon. So a zero tension, if you have a zero tension brane, it just sort of sits at the horizon here, or it would have this geometry. Okay, so it would intersect the horizon, and then for higher tension, it gets pushed further and further back like that.
Sorry, but when you say more boundary degrees of freedom, you mean a more complicated state? There are no real new degrees of freedom, right? We're just looking at a state in.
That's right. Yeah, that's right. So it's we're making use of this Euclidean boundary CFT in order to construct a state of a regular CFT on a sphere. And so in this Euclidean CFT, we can actually introduce extra degrees of freedom, which sort of couple to the original CFT degrees of freedom. And right, probably they produce a more complicated state than you would have had. But exactly, it only affects the state. And so it's just, you know, from the Euclidean CFT perspective, then there's some measure of what boundary condition have we added, and have we added extra boundary degrees of freedom.
So there's a range of states with complexities that range from very simple, in which space-time you say would be cut off very near the horizon, to states which are sort of more complicated, in which space-time becomes larger and larger and larger.
Yes.
Is that right?
Yeah, I think that's the picture. And you know, I guess of course, one would really want to sort of understand the microscopic solutions and understand for some specific choices of these boundary degrees of freedom, what would the geometry look like? But it's a little bit different.
Sorry, relatedly,
yeah.
Sorry, relatedly, you know, there's many possible states, right? There's the whole field theories, Hilbert space was a huge class of states. Presumably, geometries can't get that. So that means that this end of the world brain would have to have a large number of degrees of freedom living on it, effectively, more or less as many degrees of freedom as the field theory itself. Is that right?
You mean if, you know, of course, some of the end of the world brains could be very simple.
Yeah, but they have to be different. Since each state is its own geometry, there have to be as many different geometries as there are states in the field theory. That's a huge number.
Well, I mean, what I'm talking about here, you know, I haven't said that all of, I mean, so far this is just a specific special class of states. So,
okay.
So, you know, the things we considered, for example, were translation invariant. So these are very special states. You know, if I choose a boundary condition, of course I could choose one that varied spatially in some way, but the simple ones we have in mind are just, you know, invariant under translations on the sphere. And so those are probably quite special in terms of the full class of possible states that you could consider.
But suppose we just free up our imagination and allow ourselves to do more general things.
Yeah, okay. So maybe there's, maybe, you know, in this way, if we consider something general enough here, we could actually come up with a basis of states for the full CFT. Yeah.
Which sounds like your end of the world brain would have to have a huge number of degrees of freedom living on it, roughly.
Yeah. Hi, Mark. Can I ask a follow-up question? So, you know, if you look at the paper of Turkoglu and Malacena, so the entire basis of states, the spin eigenstates.
Yeah.
So if the end of the world brain has to contain information about the various spin eigenstates, there's a lot of them, and the tension is just one number. So how do I incorporate, how do I model the end of the world brain so that it contains that much information about the spin eigenstates, let us say?
Yeah. So I mean, of course, the actual, yeah. Okay. So I mean, if we look at this geometry, remember, the end of the world brain is just taking the place of some complicated way in which the 10-dimensional geometry caps itself off. And, you know, so I guess there are many possibilities for that. If you push this brain further and further out, right, then what you're getting behind the horizon is, it's like you're recovering. As it goes further and further out, you're getting almost an entire ADS space again with a cutoff. And you know, those are the degrees. If you could actually, you know, have the all the possibilities there for geometries behind the horizon, I guess that is a, you know, all the states of a CFT up to some cutoff.
Is it? Can I just ask a question? So
Yeah.
you know, we already have.
Yeah.
This is Spencer. Hi. So we already have the Kurkulu-Maldacena states described on the green line of your diagram in the lower left.
Yeah.
Am I to understand that, as you said, actually, if you push the red line, the end of the world brane, more and more towards the left, you will create another space-time actually. So is it that this end of the world brane is in some sense a reflection of the conformal field theory on the other boundary?
Well, I mean, all of the degrees of freedom are here.
Yes.
We have
But
many
then what
states.
yes.
So we have many states of the CFT that you know, from the perspective of this outside the horizon geometry, they just look like a Schwarzschild black hole. And I guess what I'm saying is that at least for so I'm not sure if, you know, this is going to apply to some whole basis of states, but at least depending on which way we choose to end this this space here, you're going to get many possibilities for what it could look like behind the horizon. So what I don't really know, I mean, I'm not sure whether I should think of there being a very large number of states that would give you a completely geometrical picture like this. So far, all I'm suggesting is that at least for some special class of states where maybe these are translation invariant, I can have a geometrical picture where there's something behind the horizon and the space-time is geometrical up to some end of the world brane. I mean, maybe you can actually get, by considering boundary conditions that depend on space and everything, maybe it's possible to get a full basis of these things and understand that somehow. But yeah, I'm not sure if one should think that.
But Kurkulu-Maldacena did have a very large class of states. That
Absolutely. Kurkulu-Maldacena certainly had a basis of states. They had all of the states, and in their picture, I guess the end of the world brane should capture that. So I'm not sure it's totally analogous. Although I should say, Jamie Sully was telling me about some work he's doing with John Cardy, where you know, I guess what they're thinking about is not just single boundary conditions here, but sort of the possibility of, so a more complicated thing you can do, instead of just having a single translation invariant boundary condition. So that, you know, there's a set of those things. That's certainly not enough to make a basis. But what Jamie was suggesting is that if you allow boundary conditions in certain regions, as well as these boundary condition changing operators. So just having one boundary condition in some region and then another boundary condition in some region and so forth. So that gives you, that's a way to have things spatially inhomogeneous, and that gives you many possibilities. And so they're investigating the possibility that might actually give you sort of a complete set of states for your CFT. And so that's sort of suggestive of, you know, maybe some more complicated structure for these branes, where sort of in some regions it could be have some local physics, and in some other regions it can have some other local physics.
Sorry, one last question along these lines.
Yeah.
You're suggesting that, you know, in many typical states at least, where you might have expected smooth space-time from the Schwarzschild geometry, you actually hit something very different, though behind the horizon.
Yeah.
And I was wondering whether one might be able to see this classically. I mean, perhaps it's true that you take a generic perturbation of Schwarzschild geometry, and behind the horizon something funny starts happening, more or less generically. Do you know if that is possible, whether it's ruled out?
Yeah, I'm not sure. I mean, these are of course special geometries because they're time symmetric. You know, I guess Yeah, I mean, all I can say is that we have a simple sort of gravitational setup, and then there are these solutions in that setup that look like the black hole with some behind the horizon region, and then our setup gives you a way to end the space-time, and we find the solutions. And I imagine if you now did the same thing and add a scalar field, I suspect that you would find similar solutions, but now maybe it would look like there's some scalar matter coming out of the black hole and it falls back in the black hole. So just from the classical gravity point of view, it seems to me that there are solutions like this. One of the things I was interested in, I started talking about this a little bit with Benson Way, was could we come up with maybe by adding an extra circle like in the bubble of nothing, could we actually find some solutions that more or less look like this without actually having to invoke this end of the world brain. But it seems interesting to just understand what's possible at the classical level.
Yeah, just taking a generic initial condition for Einstein's equations, could it be that these generic initial conditions lead to large curvatures or very funny stuff, generically somewhere behind the horizon? That just classically I don't really know, but I'm not sure this has been studied very much.
Yeah. I don't have a useful thing to say, I think.
Okay.
So Mark, I had a question.
Okay.
So this, so let's just situate this discussion just to clarify things in my mind in ADS 5 cross S5 and in n equal to 4. So if you have something like a D3 brane which is coming into the bulk, it seems to me that your states that you're describing in the boundary theory in n equal to 4 are something like operators with large conformal dimensions, right? At least order n, maybe not order n square, but let's say order n or some.
These states would be order n square. I mean, the state that I'm talking about here would be something dual to a classical black hole geometry. So this is energy of order n squared.
Okay. So on the CFT side, let's say this state that you're talking about would be some large conformal dimension. And is that right? So am I to understand that this kind of a brane description is there for states of that kind, that things which are close to black hole states, as you say?
Yeah, that's right. I mean, we could actually. So if I can draw this. Right. Well, okay. Let me just. So the insertion of this boundary, you could think of starting from a disk. If you want to think of this sort of state operator correspondence, you can imagine starting from the disk, and then the boundary is now like cutting. So the disk would be the vacuum, and then the boundary is like cutting a hole out of the disk and putting some boundary conditions. But there should be something like an operator product expansion for the insertion of that boundary, and then that would be some sum of operators, and those things would have not just one dimension but some set of dimensions, and typically those would be of order n squared. And so our state here, it's not an energy eigenstate, so it's time dependent, and so that would be reflected in having some range of dimensions for this operator product expansion of our boundary insertion.
So can I think of this as starting with some order n square energy state, something which is like a black hole? Let's say there are many of them, and then over that you are kind of exciting one of the scalars or something, like say Coulomb branch. You're going, of course, I think you're thinking about in the sphere. So if you excite it, it will evolve in some way, and.
Yeah, I'm not sure I would think. I mean, I think this is just a way to write down some particular high energy state that's one of the black hole microstates.
Okay. Do you have an excitation over that black hole microstate, right? So something which is not an energy eigenstate. Some excitation where the
Yeah,
brain,
it's not it's not an energy eigenstate. I mean, it is a state with a large energy expectation value if this tau 0 is sufficiently small. It's a pure state, so it's a particular state. It's translation invariant.
Okay.
Yeah.
Okay. Yeah. So the kind of states that are described by this description, are they all of this kind, or I mean, this goes back to this question that many people had asked, in the sense that in what sense are these states complete? I mean,
Yeah. So again, I mean, I think in order to get a complete set of states with a construction like this, then you would have to at least do something like consider inhomogeneous boundary conditions, or maybe they could be locally translation invariant, like Cardy and Jamie Sully were suggesting, or you could just imagine some sort of sources that were spatially dependent or something like that.
thanks.
Any more questions?
So Mark, this paper by Stanford, Pennington, and Schenker, had this sort of toy model of black hole evaporation with an end of the world grain, sort of, I think, conceptually similar to what you're describing.
Yes.
With many degrees of freedom. Yeah, I just wanted to ask whether that's roughly the same ballpark of ideas.
Yeah, I mean, it's very parallel. So when we were okay, so basically, just to put that in the context of that, originally, so there were a couple of, I guess it was sorry, where am I? Yeah, this group. So there was this paper by Pennington, and then this paper by Almeri and Engelhardt, Maxfield, and Marolf. So that second one considered just like 2D gravity, and then coupled that to some non-gravitational system, and then you can think of the 2D gravity as coming from some SYK model. And then it would be like an SYK model coupled to some non-gravitational system. And so that's sort of a picture like this one, this one here. So you could imagine having some SYK models here, and then some non-gravitational system. And then I guess what Almeri, Majan, Maldacena, and Zhao did was to say that I'm not very good at, okay, there it is. This pen seems to appear and disappear at random. Yeah, so the original picture was just, okay, we have like a 2D gravity, something like JT gravity, and then some auxiliary system. And so it wasn't sort of discussed very much, but that you can imagine is coming from some SYK models coupled to an auxiliary system. And then the later Maldacena paper said, well, why don't we, instead of just JT gravity here, why don't we have JT gravity coupled to some kind of cutoff holographic CFT, and let's make this holographic CFT as well. And so that was sort of our motivation, was to come up with a picture that's like this, but maybe a little bit closer to ordinary holography. And so we ended up sort of thinking about this picture. The calculations we were able to do most simply were in 2 dimensions, and so that was actually quite similar to this doubly holographic model, and then sort of later developments of the Stanford group and also the IAS group were basically kind of pointing out the relevance of these Euclidean wormholes in the entanglement calculation. So that sort of also shows up for us. I emphasized that in the first set of slides, that this phase transition and entanglement entropies that kind of lies at the heart of all these calculations. There was also kind of a Euclidean wormhole story there, where if you do the gravity calculation of the replica partition function that we ultimately need for our calculation, then you get something like a Euclidean wormhole, but it's the multi-boundary wormhole is the end of the world brane.
I have a question.
Yeah.
Okay, can you hear me? Yeah, okay, sorry. So just to, maybe I'm just confused about this, and this might not be a good question, but in the difference between your model and the Malassina model, the doubly holographic model, is that it seems that the end of the world brane in the bulk is still a representation of the boundary conformal field theory. That, I mean, the degrees of freedom which are holographically dual to end of the world brane are still the CFT degrees of freedom. So somehow in their model they do have two different systems. There's SYK and then there is CFT. In your model there's only CFT, and end of the world degrees of freedom are only holographically dual to CFT. So somehow this structure
in
of
our model, I think what we wanted is some lower dimensional. The thing I think is nicest is to think of some lower dimensional CFT with many degrees of freedom, and now I add in a higher dimensional CFT with sort of fewer local degrees of freedom. So the thing that's playing the role of SYK. Yeah.
Is there any limit in which SYK can be just directly, because I'm just saying that this GB doesn't really have anything to do with SYK. It's still the counting degrees of freedom of the bath itself, right? It's not, I mean, we can probably interpret it as black hole entropy maybe, but I'm saying it's still just one system, and it's a boundary conformal field theory. I don't have any other system. So even the GB quantity should just belong, sorry. Yeah.
Okay. I mean, I think the nicest model, which is not, we in the end didn't fully study this thing, but I think the nicest model is where you have, let's say we have a 2+1 dimensional CFT that's holographic and it's living on a sphere. Okay. And now I can think of, and that has some kind of central charge or some number of degrees of freedom. Okay. And that can have high energy states, which are dual to some black holes. And now I think about adding in, having those degrees of freedom as the boundary. So that's playing the role of the SYK degrees of freedom. And we can think of those as being now the boundary degrees of freedom for some added on to some higher dimensional CFT with kind of relatively fewer local degrees of freedom. And that would be the higher dimensional thing is the analog of the auxiliary system. So it's still, yeah, I mean, so I think in some examples you can, even though they're coupled, you can kind of think of starting with the degrees of freedom that are describing your black hole and then adding in some new degrees of freedom.
I see. Okay. Yeah. So is there any limit in which I can actually show that like a CFT coupled to a higher dimensional CFT in some limit can be just thought of as a boundary conformal field theory of this higher dimensional CFT? Somehow I freeze one of the CFTs.
I mean,
that's the picture.
I think in the IR, I mean, just in general, if I had some 2+1 dimensional theory, and then I coupled it to some higher dimensional quantum field theory, You know, in the IR, that thing would flow to something that's conformal.
I see.
So,
Okay. All right.
yeah.
Thank you. Thank you.
More questions? If not, let's thank Mark again for a wonderful talk. Let's clap.